27, 41 spansel permutations. So we are giving a zero-index integer array nums containing n distinct positive integers. So a permutation of nums is called spansel. So this is going to be the formula. So from the index 0 to n minus 1, as you can see that this is I less than n minus 1. So this is for example, we have 3 numbers, 1, 3, 5 maybe. Yeah. So this is going to be the final one. It is actually n minus 2. We want to check n minus 2 with n minus 1. Yeah. So this is also okay. We just need to check this pair and this pair. Yeah. So if it meets the condition nums I modular nums I plus 1, or nums I plus 1 modular nums I equal to 0. If it meets either one of them, so it means it is okay. It meets the conditions. It is a spansel permutation. So we're gonna return the total number of spansel permutations. So the answer is gonna be a modular 10 to the power of 9 plus 7. And for this problem, actually, it is very similar to the previous problem we solved before. So for example, 526, it is the beautiful arrangement. The only difference is that there's no sequence for this problem. It just needs to meet the formula. Yeah. But for this problem, there is a sequence for the neighboring two numbers, nums I and nums I plus 1. If it meets the condition, it is a spansel permutation. But the idea is going to be the same. We're going to use the same idea from previous problem to solve this problem. Let me just copy the same code. Yeah, because I'm going to use the same idea, I don't want to write the same code again. But basically, I need to change a lot of things. Yeah, because we are giving a number nums. From before, it is just a permutation of 1 to n. Now we have a nums array, and we have this kind of a formula. It is two numbers, nums I with nums I plus 1. If it meets the condition, we're going to call it as a permutation. But I mean, all the numbers should meet the condition. So for example, 3 and 6, 6 and 2, it is okay. 2 and 6, 6 and 3, it is also okay. So there are only two permutations. We're going to use a beta dp to solve the problem. Basically, the idea is we have nums from beginning. We want to check all the permutations. If we want to use brute force, basically, we cannot solve the problem. Yeah, because maybe this. Let me check the number of this. Yeah, so the length is 14. Basically, 14 times 14 factorial, and we also want to check the two neighbors times another 14. Yeah, because we need another loop to check the two neighbors if it meets the condition. As you can see, it's going to be a really big number. Definitely, we cannot solve it. That is why we're going to use a bit dp. Because bit dp, the time complexity is going to be 14 squared times 2 to the power of 14. Yeah, because basically here we cannot change it. But 14 factorial, we can change it. Normally, bit dp can be used to solve the permutation problems. Yeah, so this is just a spansel permutation. It means we just need to check the formula. So the idea is that we want to check it from the beginning. We're gonna check it as an empty set. Now we want to put the numbers inside the set one by one. So for example, from the beginning there's nothing inside the set, and we can put a number 2 because there's no limitations. And I want to put the first number 2 inside. Definitely I can put it inside. Yeah, or I can also put another number inside. Maybe I can put a number 3 inside my set, or I can also put a number 6 inside the set. Yeah, because for the first one there's no limitations. Because this one gonna be my first number, or this 3 gonna be my first number, or this 6 gonna be my first number. Yeah. Now for the second number, definitely I have some permutation. I have some constraints. So for this number 2, can I put a number 3? No, I cannot, because 2 is not modular by 3. 3 is not modular by 2. I cannot put 3. 3 is not. So what about I put 6? 6 is okay. Yeah, because 6 is divisible by 2. So after that, can I put other numbers? There's no other numbers because only 6 and 3 and 6. So after 6, can I put another number 3? Yes, I can. So this is one possible case. Now we want to check this one for 3. So if I take out the 3, can I choose a number 2? No, I cannot choose number 2. It is the same idea. Can I choose a number 6? Nums I modular nums I plus 1, or I plus 1 modular nums I equal to 0. And let me just check this one first. Yeah, it is a possible result. So because here I just cannot say that, I just want to use these areas. Basically there are 2 permutations, so 3, 6, and after that I'm gonna have a 2 because 6 modular 2, it is also okay. Now we want to check this 6. I can choose a 3 definitely, or I can choose 2 definitely, it is okay. But after that, can I choose 2? No, I cannot. After 2, can I choose 3? No, I cannot. So how many cases? This is one case, this is another case. There are only 2 cases. Yeah, so this is the recursive function for us to understand the problem. But finally, we're going to use the bit dp. But the idea is just like that. It seems we need to remember the previous number. And in this way, we're going to define our recursive function. It means definitely inside we're going to have a previous number. So for example, from beginning, this is 2. I'm going to use a minus 1 as the previous number. This previous number must not inside my numbers. Yeah. So I'm going to set a minus 1 because all my numbers is from 1 to 10 to the power of 9. And this is according to the concrete, and you can check it later. Yeah, I mean just from the concrete, it is always positive integers. Now, I'm going to set it as a minus 1 from beginning. So from beginning, if it is a minus 1, I'm going to directly use the 2, 3, and 6. And for the next one, I have a previous number of 2. I can use the 2 and 6. Yeah, this is okay. Another variable is the state. I want to use a state to record all the state because I'm not sure if this 2 is checked, or this 6 is checked, or this 3 is checked. So if it is checked for the next iteration, I don't want to check that. And if I have the result, and also for the next iteration, I don't need to check the result again. Yeah, because this is basically a recursive function. Basically, there's a lot of duplicates, and we want to use this kind of a bit dp as my state to avoid the duplicates. And only in this way. And how many states? 2 to the power of 14. And how many this previous number? It also 14. And how many for loops to check? It is another 14. So that is why 14 squared times 2 to the power of 14 is for the bit dp solution for the problem. Yeah. Now the problem comes to how can we use bit dp. And as this is just a permutation problem, and we can use the bit dp easily. So for the bit dp, we're gonna set always, for example, 3 numbers. For those 3 numbers, we're gonna set it to be 0. And if we have this number, so for example, we have this number 2, it is from the index 0. So we're gonna set this bit as 1. If we have this number, next one for the 6, we're gonna set the third number. Yeah, this one is as 1. Or maybe for the next one, we're gonna have a 3. We're gonna set this bit as 1. It is just according to the different sequence, but finally this is my final state. If I have this final state, so I'm gonna return a 1. So this is because I've found a possible result, and I just wanted to check how many different kind of these permutations and also meet the formula. Yeah. Now let me just change a little bit to the previous code. I want to have a number n because this is gonna be my state. It's going to be the length of the nums. And now my state is going to be the 1 shift n minus 1. So for example, if this n equal to 3, and my state is going to be 7. I just want to check how many states of 7. Now I also want to, yeah, let me check. Yeah, so for the DFS function, I need a state, of course, and I also need to have a previous number. So my previous number gonna be starting from -1. As the result can be really big, I would to have a mod. It's gonna be 10 to the power of 9 plus 7. This is according to the description. This means the final one I'm gonna use a mod. Now I would to, I mean, if you don't understand why I'm gonna do it like that, I suggest you check the problem of 526. I've also posted a video, and later on I'm gonna put a link for the previous problem for that video. And basically, if you don't understand that, you can check this video. Maybe this is explained more detail about why the bit mask or why the bit DP works for this kind of problem. Now I want to check the state, and the state is okay. I don't need to change, and this one definitely I don't need it because this is just an index. Now this is my result. I need it, and I want to check all the different numbers. I don't need to check the permutations, so I need to use index I num for enumerate the nums. Yeah. So this is the index, and this is the current num. And the index is used for the bit DP. I want to check, basically there are 3 indexes. So for this number, the length is 3. So this is 0, 1, 2. This is just for the positions. I just want to check those 3 bits if it is always to be 1. If I can get this kind of a state, I'm gonna return a 1 from here. Yeah. Now I want to put it inside my state. I want to check if I have it or not. If I don't have it, definitely I want to put it inside. Yeah, so here I need to change it to I, because the I is just the position of the number. So for the first number 2, it's gonna be I equal to 0, and 1 left shift 0 positions is gonna be still be 1, and I'm gonna check with the state. The state is 0. And definitely 0 and 1 is going to be 0. So I want to put it inside. So here I want to put this bit inside. Definitely it means I want to put that number inside. And here inside I just need to change it to the formula here. As we also have a previous state, previous number. So I want to check if this previous number equal to -1. So I'm going to execute and the result and put it inside of the result. Yeah. Or nums I, so nums I plus 1. So currently I wanted to check my current number with the previous number. So this nums I is the previous number, this I plus 1 is the current number. So my current number is num, and the previous number is prev. If this is equal to 0, or the previous number modular my current number equal to 0. Yeah. So if I meet either one of those 3 conditions, definitely I want to put it inside, and this is going to be my final result. Yeah, as you can see, I didn't change too much for this kind of permutation problem. So normally for the permutation problem, if it is a Spencer permutation or other kind of a beautiful arrangement, beautiful permutation, or the permutation, definitely we can use a bit DP to solve the problem. Now let me run it. Something wrong. Yeah, it should be inside the enumerate nums. I didn't use the previous, so the previous should be the current num. Yeah, for the next recursive function. Yeah, now as you can see, it is okay. Now let me submit it to check if it works. Yeah, as you can see, it works. It takes more than 2 seconds. This is because this number 14 square times 2 to the power of 14 is going to be a big number. That is why it takes a time. Yeah, so let's just check that number, because that is the time complexity. 14 to the power of 2 times 2 to the power of 14. I think this is going to be a big number. That is why it takes the time. Yeah. So yeah, it's going to be 3 times 10 to the power of 6. So this is why it takes the time. Yeah. basically if this number is 15, definitely we cannot solve it. So this is why they set it as n equals to 14. Yeah, because if we use 15, it's going to be 10 to the power of 7 or 8. Definitely it's going to be a very big number. So let's just use 15. And here we're going to use 15 to check the final result. So for this number, it's going to be 7 times 10 to the power of 6. Oh, so this is also okay. If we set it to 15, it is also okay. Yeah, so this is just for fun. But the basic idea is to use base DP to solve the problem. Thank you for watching. See you next time.